Hello everyone. In this lecture, I'm going to talk about transmission electron microscopy. Now this transmission electron microscopy, or in simple we say TEM, is a very powerful tool for, we use them in material science, especially in nanoscience. So this transmission electron microscopy is used to produce images from a sample by illuminating the sample with electrons within a high vacuum. So it's very similar to SEM in the operation, but in the SEM, what we do, we bombard the sample with incoming high energy electrons, and then we analyze the outcoming signals from the top side of the samples. Detectors are based on top of the on the top side of the sample. So some signals escaping from the top side of the samples are analyzed in the scanning microscopy. But in the transmission electron microscopy, the detectors are below the sample. So electrons has to go through the sample and reach the detector. So so the sample, the whole TEM column is kept under high vacuum, and detectors are situated below the sample to detect the electrons that are transmitted through the sample. So you can see here are some gold nanorods and gold nano cages imaged using TEM. Here, if you can see, this much of length is 0.1 micrometer, that is 100 nanometers. So if you just try to figure out the nano cage size, this is around 50 nanometers. But if you look at the gold nanorods, this is 0.1 micrometer, that is 100 nanometer is given by this size, but if you analyze it, these are much lower than 100 nanometers. So when the particle or the structure sizes are much lower, TEM is a good solution for that. Here, as I told you, a high energy beam of electron is shown through a very thin sample. Now in the SEM, we didn't have this issue, but for the TEM, the sample should be very thin because the incoming electrons needs to be transmitted through the sample. So we keep it thin as possible. And the interaction between the electrons and the atoms can be used to observe the features such as the crystal structure, features in the structure like dislocations and grain boundaries. Those things we can observe using TEM. And also we can analyze chemical analysis. We can perform it using TEM. And to study the growth of layers, their compositions and defects in semiconductors, those are very common applications. High resolution TEM, which means we zoom in, and for these things, the sample should be very thin, like less than 100 nanometers. High resolution can be used to analyze the quality, shape, size, and density of quantum wells, wires, and dots, and even the crystal planes. Now, the basic difference between the light microscopy and here this should be TEM. I'm sorry about this mistake here. This should be TEM. The difference between the LM and the TEM is the light microscope, both the source, here the source of light, here the source of electron source is both situated at the top of the setup. Here the LM, the sample is shown using this light beam, and light beam is focused onto the sample using a condenser lens. Here the electron beam is first accelerated using a high potential, and then it is focused onto the sample using a focusing lens, or we call them condenser lens. And then we have the specimen here, and then from the specimen, the light, diffracted light, it is or the scattered light is focused using an objective lens towards the eye. Here also the transmitted electrons are focused using a projection lens, and then instead of eye, here we have a detector which is sensitive for the outcoming electrons or whatever the signals that arise. So this is a very simple schematic of the TEM. So the advantage of TEM over light microscopy, obviously it has a very high resolution at very high magnification. So as you all know, resolution can be defined as the smallest distance between two closely opposed points. Now imagine you have 2 points. If your light microscopy has a good resolution, that means the distance between these two particles are larger or comparatively larger than the wavelength of the light that is used to image. Then what happens? You can easily distinguish there are two particles. But what happens, they are like these 2 points are situated very closely. Then your wavelength, let's imagine the distance between these 2 points and the wavelength are comparable, like they are in the same level. Then what happens? This light wave starts to diffract. And when it diffracts, what happens? It starts, I mean, if it's just a point-like particle, what happens? This light will start generating diffraction rings around the particle. And two particles are closely situated, and then they start generating these diffraction rings. What happens? Because of these diffraction rings, they start to overlap, and you won't be able to see two separated points, but what you see is a blurred rings. And if they are like very closely situated, very closely situated, and your wavelength of light is much more bigger, like let's imagine you're using a yellow light. Yellow light has a wavelength around let's say 450, 400 something. Then what happens? Imagine your particles, the distance between these two particles are 50 nanometers. So when the yellow light tries to, like when you try to image, then what happens? The wavelength is now much bigger than the opening between the two particles. What happens? It starts diffracting. The smaller the separation or the window, it diffracts a lot. Then what happens? Only you will see a big blob, not two particles are identified separately. So in such cases, we use electron microscopy. Why? Compared to the photon with, let's say, 1 electron volt, the electron with the same energy has a much lower wavelength. So you can easily differentiate. So that's why the resolution is very high at higher magnification. So the best resolution possible in light microscopy is about 200 nanometers, where a typical TEM has a resolution better than 1 nanometer. So you can easily image atomic, you can get atomic resolution using high resolution TEM. And TEM, you can get the structural information easily. If the material being viewed has a periodic structure like a crystal, you know, in a crystal, the atoms are arranged in a periodical manner. Then what happens, these electron beam can interact with that crystal plane structure such that now the atoms acts now, because in this way the atom, normally the atomic atom distance, the atomic interplanar distance in around few angstroms. The highly accelerated electrons have a much lower wavelength. These electrons act as waves. They don't behave as particles. We can consider them as waves. And these atoms, what happens? They act as diffraction sites. So these electrons, when they diffract by the atoms, they can be recorded, and this diffraction pattern can be used to analyze the crystal structure of that material. And then we can use microanalysis. As I told you, we know that when the incoming energetic electrons interact with the sample, these electrons will interact and emit characteristic X-rays. These X-rays can be examined and we can get the compositional idea about the sample using TEM, just like the SEM. So the main difference between the SEM and TEM, as I told you, SEM uses signals or the electrons, like secondary electrons, that are escaping from the top side of the sample. But in the TEM, it uses electrons that are transmitted through the sample. So here you can see the first one is pollen grain. Pollen, you know, paraga in Sinhala, pollen grains, small pollen grains weaved under SEM. You can see they are like these, like lychees or rambutan or like coronavirus. But when you observe them using TEM, what you see is not the topographical image, but it's more like a cross section. It's yeah, it looks more like a cross section of the pollen grain. So this is very basic thing. TEMs are 2D projections. Now you can see this is the incoming electron. These are, let's say, some materials inside your sample. So your sample is very thin, and these are located inside the sample. When they are bombarded with incoming electrons and they are imaged using the electrons that are reaching from the other side of the sample, you will see these things looks like shadows. They are 2D projections of the sample. Right. If we talk about the SEM, it has several parts. Like first on top, we have the electron source with the electron gun. And then we have the electron column where it contains all the electromagnetic lens system. And then you have the sample holder or the stage. And then below we have the detectors. We need a water chilling system because we use highly accelerated electron beam in ultra high vacuum. So it always requires cooling. And then we have the specimen and the sample chamber. Then we have a main control panel and other operational items, then controls, and we can capture the images. So electron gun, as I told you, very similar to the SEM. Electron gun here produces the electron beam, and it is situated at the very most top of the TEM. And types of gun is very similar. It is field emission TEG, that is thermionic emission electron and field emitted electrons FEG, and Schottky emitted electrons SEG. So this is basically the very much same that I described earlier in the SEM, so I'm not going to go into details. So in the electron column is made up of the gun assembly at the top, and column is filled with a set of electromagnetic lenses which can control the beam path, beam diameter, and then it has the sample port and airlock. Here you can see the sample port here. You can open it and the sample, the stage will be coming out, and you can load samples there, and then you push it in and lock it. So it has an airlock and a set of apertures that can be moved in and out of the path of the beam so that you can get the desired beam diameter. So the electron column, all the contents of the columns are under ultra high vacuum. As I told you, the main reason for this is you don't need to lose your electrons to air molecules, because if air molecules are presented inside this electron column, these highly accelerated electrons will bombard on these air molecules, and they will start ionizing the gas atoms. And when we allow that to happen, what happens? The electrons will lose their energy to air molecules, and that is not desirable for us. We need the full electrons to be occupied. Like we need them fully focused onto the sample to get the best resolution. Because if we lose electrons, that means we're going to lose the intensity of the beam. At the end, it will inadvertently, it will definitely result in degrading the quality of the sample. Right, so this is the aperture holder, and this is the aperture strip. These apertures can be easily removed from the beam part by the user. The apertures are located within the aperture strips, typically consisting of a strip of molybdenum containing a sequence of different sized holes that allow modulation of the beam to different degrees of precision. So depending on your application, you can fiddle with the aperture holder to get the desired beam size. So the magnetic lens system, very, very similar to the SEM, because here also we use highly accelerated electrons. Electrons are sensitive to magnetic field, therefore we are using an electromagnetic lens here. So within the column, the electromagnetic lenses shape the electron beam which travels in a spiral trajectory. Each lens is constructed of a coil of copper wire through which the current runs. So when the current runs through these copper coils, what happens? It generates the magnetic field, which will in turn control the electron trajectory. So there is a hole in the center through which the beam travels. So here you have we have the hole where the electrons will enter. So here, as I told you, we have the soft iron pole pieces that will, the coil is inside and it generates the magnetic field, and the soft iron pole pieces will prevent these magnetic field escaping everywhere, but it has a small opening here. So the magnetic field is now coming out from this pole piece. This is what called the pole piece. Like if you remember, I talked about this pole piece in the SEM also. Okay, so yeah, this electron beam will then we can like control it. We can focus it onto the sample. Then the outcoming electrons will be again focused onto the detector using a projector lens, or it's another sort of electromagnetic lens. So this is just a schematic showing you how optical lens work, and this is a schematic shows you briefly how electromagnetic lens is used to control the electron path. As I told you here in the SEM, TEM also, it has a specimen stage, and specimen stage helps to stably support the specimen and move it around smoothly. And this can also perform horizontal movement, that is moving along XY plane to select the field of view. Vertical movement, so you can change the image resolution if you want to magnify, but you can move it up, and then you can change the depth of focus and then get the desired resolution. So you can tilt the specimen to get the cross-sectional view, and you can rotate it if you want. And as I told you, to perform all these things and get a very good quality image, you need to make sure that you you position your stage at this EU-centric position. Right. So the electron matter interactions happening in the TEM will be the source to generate the image. So obviously some of the incoming electrons are absorbed as a function of the thickness and the composition of the sample. And then we can use this concept to amplitude contrast imaging. So the outcoming electrons will have their amplitude is different. So yeah, we can get that as a function to get the image. The other electrons are scattered over small angles depending on the composition of the specimen. This we use as the phase contrast imaging. And in crystalline specimen, the electrons are scattered in very distinct directions. As I told you, in a crystalline material, atoms are located in a periodical manner. So they more or less act as a diffraction grating, and these electrons are diffracted or scattered in very distant directions, and we can analyze them to get the idea about the crystal structure. We call it diffraction contrast imaging. And electrons which have lost an amount of energy because of the interaction with the specimen, we can detect by energy loss spectrometer. The beam of electrons from the electron gun is, as I told you, focused into a small coherent beam by the use of the condenser lens, and then this beam is restricted by the condenser aperture, which will by default exclude the high angle electrons, only allowing very highly directional beam coming out. The beam then strikes the specimen, and part of it are transmitted depending upon the thickness and the electron transparency of the specimen. This transmitted portion is focused by the objective lens into an image on a phosphor screen or charge coupled device, CCD camera. So this is the amplitude contrast imaging. Optional objective apertures can be used to enhance the contrast by blocking out high angle diffraction electrons. Now, the outcoming electrons are diffracted in everywhere, but if you want to, if you don't want the highly diffracted ones, you can neglect them, and then you block them, only allowing the electrons with a defined, within a angle defined by you, and then you can increase the quality or the contrast of this image. The image then pass down the column through the intermediate and projector lens, and it is enlarged all the way. So the image strikes the phosphor screen and light is generated, and that is taken through a photomultiplier tube and then goes to an amplifier. Then the user can view the image. The lighter areas of the image represents those areas of the sample that more electrons were transmitted through. So if there's a comparatively dark area, that means comparatively higher number of electrons are absorbed in that area. So you know, just by looking at it, you see there is a contrast in the brightness. So just by looking at it, you know there is a different material there, or either sample thickness is lower or a material composition is different. So in the image mode, we can use for non-crystalline or biological materials. We can use this for crystalline materials as well. We can use the amplitude contrast or phase contrast imaging. But if you have a crystalline sample, it can be a single crystal or it can be a polycrystalline sample. You can use phase contrast as well as diffraction contrast. As the electrons pass through the sample, they are scattered by electrostatic potential set up by the constituent elements in the specimen in the diffraction mode. After passing through the image, the specimen, they pass through the electromagnetic objective lens, which will focus all the electrons scattered from one point of the specimen into one point in the image plane. So the electrons scattered in the same direction by the sample are collected into a single point. And this is the back focal plane of the objective lens, and that is where the diffraction pattern is formed. So you can see here it's a silicon, it's a crystalline sample. So here is the parallel incoming electron beam, and you have the sample here. Because this is a crystalline sample, they are periodically arranged atoms. What happens? These electrons will start to diffract. And then we have the objective lens. And here is the diffraction plane, or we call it back focal plane. Then what happens? These diffracted rays, or in electron beam rays, will be focused using objective lens. And then what happens? They are collected. Now here, this is diffracted from the same point, these electrons. The electrons diffracted from the same point are collected on the image plane on the same point. And it will reveal the crystal structure. So you can see the periodically arrangement of the atoms in here, the high resolution SEM, and this is the selected area diffraction pattern. You can select an area and get the diffraction pattern of that, and the crystallinity will shows you a very beautiful dotted pattern. By analyzing this dotted pattern, we can say whether this is a single crystal, polycrystalline, or amorphous. We will see how we're going to do that in the next few slides. It's there, we'll come to that. So methods of specimen observation, we have bright field imaging. Some area of the sample scatter or absorb electrons and therefore appear darker. Other areas transmit electrons and appear brighter. So the bright field image appears as a shadow of the specimen. In the bright field image, the objective aperture is used to select the unscattered electron beam. So by doing so, the scattered electrons are excluded from the image, and then this aperture enhances the contrast in the image. We will look into this bright field and the dark field, the difference. So here you have the zinc oxide crystal. We observe using bright field imaging. So the object appears as dark and the background appears as light, because we allowed in the bright field image, the objective aperture is used to select the unscattered electron beam. Unscattered electron beams means these electrons, they don't, even though they go through the sample, they don't get scattered. That means they don't get much interacted with the specimen. So here we have isolated the zinc oxide crystal. Here we don't have anything. So electron is directly gone through the sample and reach the bright field aperture and used in the imaging. So it appears white or bright because it appears lighter because more electrons are there in there. And here, because we have the zinc oxide crystal, the electrons can be, when they pass through this, they will definitely get scattered by the zinc and oxygen atoms in the zinc oxide crystal. And because they are scattered, they scatter in a different angle. They all are removed from the imaging. Therefore, it appears dark. So this is bright field imaging. Here also we have a rat's liver, where the sample is thinner or there's more probability of getting unscattered light, appears brighter. And if there's a thicker film, or if there's if the sample is thicker, or if you have a material which absorbs more light, that means more electron is absorbed, or incoming electrons are scattered in a large way, they appear darker. Dark field image, it's the other way around. So this is produced by excluding using the primary aperture. So they use the primary aperture, and by doing that, they exclude the primary unscattered beam from the image, collect below the sample. So this will remove all the unscattered electrons. That is the primary beam coming transmitted through the electron beam. Unscattered, they don't lose their energy, they don't deviate from their original path. These electrons are removed. Only the electrons that are interacted with the sample will be imaged. So this is the same zinc oxide crystal that we observed earlier. Here you saw under bright field imaging, it's like this, but in the dark field you don't have the background because it's black, because unscattered electrons are now removed using the primary aperture and only allow the interacted electrons to come through. The image is produced by only using the scattered electrons. Regions where no scattering occurs, such as where the primary electron beam passes straight through the sample, appears black. Likewise, the areas around the sample. And this kind of imaging is useful in studying crystal defects and for the imaging of specific crystallographic phases. So you don't want unwanted unscattered electrons. All you want is to get an idea about the interacted the electron, the signals that are generated within the sample. So you remove all the unscattered electrons and get the relevant information like crystal defects and crystallographic phases. So this is, we come to the diffraction imaging. So as I told you, in a crystallographic material, the atoms are periodically arranged. So incoming electrons will see an array of atoms, and they will be acting as a diffraction grating for these incoming electrons, which behaves as waves, and then they get scattered or diffracted. So this is actually the basic principle behind this is the Bragg scattering, or we use the Bragg's law to analyze this. And then the Bragg scattering as the beam pass through the crystalline sample. If a selected area diffraction aperture is inserted to delimit the region of interest, so you can choose where you want to get this diffraction pattern. So you select the area and you delimit the region of interest. Then an image created below this sample in the region called back focal plane. This is seen as an array of dots or set of diffuse rings. So depending whether it's a polycrystalline or a single crystal, that will either appear as dots or rings. This informs the viewer about the crystal structure of the sample. So this is the spot diffraction pattern of neodymium 13, calcium 07. Right. Now, just by observing this crystal, the SAED pattern, we can say whether it's a single crystal, polycrystalline, or amorphous. So if you have a single crystal, like silicon, let's say, you will observe a spot pattern like this. This is a spot diffraction pattern. But if you observe a ring pattern, this is polycrystalline material. In the amorphous, you won't be seeing the ring patterns, but you will see is a one big diffused ring pattern. So this SAED or diffraction imaging is we use them in crystalline sample like polycrystalline or single crystal samples, but not for the amorphous samples or biological samples. So the diffraction basics. Sample waved using the TEM can provide information about its structure, in particular about its crystalline nature. This is because the crystal in a lattice acts as a diffraction gradient. So you can see here, this is like a single crystal material. So atoms are periodically arranged, electron beams coming in, and they behave as a diffraction grating, and electron waves gets diffracted. Interference, now these diffracted rays will interact with each other, producing interference patterns, and so the outcoming electron beam now will have an interference pattern on it, and it travels out of the lattice, and these can be projected onto a phosphorus screen and image. You will get an image of regular dots or rings, depends on the crystallinity of the sample. Okay, so this is about giving you a very brief idea about the diffraction basis. Not going to go into details here. We are using the Bragg's law, which is n lambda equals 2d sine theta b. Theta b is the Bragg angle. N here is the order, lambda here is the wavelength, and 2 is just a constant number here. D is the interplanar distance. Right. So the unscattered electrons continue through ore to produce a central point. So unscattered electrons, they don't get diffracted. So they are directly coming down. And then when they pass through the focusing lens, they will be focused onto O. That is undiffracted, unscattered electron beam. That is the central spot. The beam is diffracted by angle 2 theta b. Theta b is the Bragg's angle. So they are diffracted angle 2 theta b. Here, this is the back focal plane image, right? Beam diffracted by angle 2 theta b produces a spot marked at G. Right, so we have the G here. This should be G, this is 2G, this is 3G. The distance between the diffracted and transmitted is inversely proportional to the corresponding lattice spacing of the sample. The beam deflection angle and electron beam wavelength are also important. So if you know the energy of the, or if you know the potential, the voltage you use to accelerate the electrons, you can calculate the energy. And by doing that, you can, if you know the energy of the electrons, you can calculate E equals hf or hc over lambda. You can calculate the wavelength of the electron beam. So once you know the deflection angle and the wavelength, you can use the Bragg's law equation and find the D, which is the crystal interplanar spacing. So TEM sample preparation is somewhat critical or crucial thing compared to the SEM, because SEM we just pop it in. If it is non-conducting, we coat it with a gold or platinum or like carbon conducting something, and then we image it. But for the TEM, you got to make sure that you obtain a very thin sample. So you can use crushing technique, you can cut it, you can use saw machine, diamond pen, or ultrasonic drill. Sometimes we all use focused iron beam as well to do the cutting. You can use mechanical thinning like grinding, dimpling, tripod polishing. You can do the electrochemical thinning, iron milling, coating, replica method. If you're using colloidal particles like particles, nanoparticles suspended in a solution, what you do, you take a portion, you dilute it like 10 times, 100 times, depending on your concentration. And you then just put a drop on the copper grid, so that if the concentration is too much, that will make the meniscus, like you will have agglomeration around the meniscus, which will make it too thick for the samples to be observed properly. So you got to keep the concentration very low. So as I told you, the TEM specimen must be thin enough to transmit the sufficient electrons to form the image without minimizing the energy loss. So the sample preparation is a very important aspect of this TEM analysis. For most electronic materials, there's a common sequence of preparation techniques. Usually we use the ultrasonic disc cutting, dimpling, and iron milling. Dimpling means it's a preparation technique that produces a specimen with a thin central area and an outer rim of sufficiently thickness to permit ease of handling. So we have thinner central and thicker outer region so that we can handle it easily. Iron milling it's a traditionally the final form of specimen preparation. In this process, we use charged ions, like mostly it's gallium. In more sophisticated ones, we can use helium, but usually we used gallium ions. Accelerated to the sample surface by the application of very high voltage, same as these electrons, gallium ions, positively charged, they are also accelerated using providing a high electron voltage. So this ion impingement upon the specimen surface removes materials as a result of momentum transfer, and thereby we can thin the sample to the desired thickness. Applications of TEM, as I told you, image morphology of the tilt sample and collect a series of imaging to construct 3D image. So usually it's a 2D projection, but we can tilt the sample and get several cross-sectional images to construct that 3D image. We can analyze the composition and some bonding differences, physically manipulate samples while weaving them, such as indent or compress them to measure mechanical properties if you have the right gadgets fitted in. You can weave frozen materials if you have a cryo stage. and then generate characteristic X-rays from samples for microanalysis. As I told you, the incoming electrons, high energy electrons, will interact and produce characteristic X-rays, characteristic for the elements inside the sample. By analyzing them, you can get a compositional idea about the sample. Then acquire electron diffraction patterns using the physics behind it is the Bragg's diffraction. You can read it more if you want to. And then we can perform electron energy loss spectroscopy of the beam passing through the sample to determine the sample composition or bonding states of atom in the sample. So there are some limitations as well. What TEM can't do is TEM cannot take color images. If you see color images, these are false colors, right? They're artificially added to the TEM. And TEM cannot image through a thick sample, so you need to make it thinner. Usually we keep the sample thickness around 100 or below 100 nanometers if you want to go for high resolution TEM. Electrons cannot readily penetrate sections much thicker than 200 nanometers. And then a standard TEM, you cannot get the topographical information like SEM do, because this is basically a 2D projection. Because it transmits through the sample, there's no way of getting surface information, but you can take several images and try to compose it in a next step to get the surface information. One more thing is TEM cannot reliably image the molecules that are mobile, charged molecules that are mobile in a matrix. Like, let's say, like sodium plus ions you have in a, they are volatile under electron beam, because the negative electron beam exerts a force on charged material. So if you have some, charged molecules that are mobile in your sample matrix, then TEM is not that reliable imaging such samples. Right, so this I will wind up the lecture. Thank you.